Hello everyone, this is Madhuri working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology. Today I am going to discuss about the losses and efficiency of a DC motor as part of DC machines course. So moving on to the first slide, before we discuss about the losses and efficiency of a DC motor, we first are going to discuss about the voltage equation of a DC motor. Then we are going to discuss about the power equation of a DC motor. Then we are going to write the what is the condition for attaining the maximum mechanical power for a DC motor. So after deriving these three conditions, that is calculating the voltage equation, power equation and deriving the maximum condition for maximum mechanical power, we are going to then calculate the losses, what are the respective losses of a DC motor, and then we are going to do the efficiency calculations, and from then we are going to calculate what is the condition for attaining the maximum efficiency for a DC motor. So first we are going to, as we see in the picture, we have an armature of a DC motor. We know that the EMF which is built up in the armature is called as back EMF. We call it as a generated EMF in the case of generator, but we call it as a back EMF in the case of a DC motor. So back EMF EB, the armature conductors, the resistance of the armature conductors is taken as RA. Here a separate DC source is required to excite our armature in the case of a DC motor, which is again quite vice versa to the DC generator. We also have a shunt field winding here. So considering DC shunt motor case in this particular situation to calculate voltage equation of a DC shunt motor. So now we have RSH as the shunt field resistance, which is connected in parallel to the armature of a shunt motor. So which is excited by a supply, DC supply with a voltage of V volts. So now if we consider V as the applied DC voltage for this shunt motor here, and EB is the back EMF which is developed in the armature of this DC shunt motor, and RA is the resistance of armature circuit, and IA is the current which is supplied to the armature circuit by the external DC source. So by applying KVL in this particular loop, we have voltage V here. So it is nothing but the applied voltage is equals to the sum of the drops or the generated voltages in the circuit. So as EB is built up in the armature, it will be the sum of back EMF plus the drop which is occurring in the armature resistance. So this is our voltage equation for a motor. So when we multiply this equation, this particular equation with IA, that is nothing but the armature current, we are going to get the power equation for the motor. So power equation for the motor will be now V into IA, which is again EB into IA plus IA square RA. So V into IA is nothing but the electrical input given to the motor or the electrical power applied to the motor. EB into IA is the mechanical power developed across the shaft of the armature. IA square RA is nothing but the copper loss which is reflected in the resistance terminals of the armature. So this is the power equation for DC motor, which is nothing but equals to the electrical power supplied to the armature is equals to the mechanical power developed at the shaft of the motor plus the losses, that is nothing but the copper losses which are occurring in the motor. V into IA, we have seen that it is the electrical power. EB into IA, electromechanical power. IA square RA is nothing but the power wasted in armature copper losses. So this is the voltage equation and this is the power equation for a DC motor. So now we are going to derive the condition for maximum mechanical power. So we have seen that mechanical power is nothing but the product of back EMF and the armature current. So from the voltage equation which we have derived in the previous case, we can write as voltage is the sum of back EMF plus the drop across the armature conductors. So from this I can write my EB as V minus IARA multiplied by IA. So this is now my mechanical power, which can be further written as V into IA minus IA square RA. So to derive the condition for maximum mechanical power, we are going to, since V and RA are constant for a given machine, that is nothing but the value of armature conductors does not change, and the supply voltage is also constant for a DC motor. So the mechanical power developed completely depends on the armature current. So now we are going to calculate the condition for maximum power by applying the differential with respect to armature current and equating it to 0. So now the mechanical power is nothing but V into IA minus IA square RA, which is nothing but the electrical power supplied to the motor minus the copper losses. So upon differentiating it with respect to IA, we will get the further equation as V minus 2 into IA into RA, which is again equated to 0. Upon solving it further, we get a condition where the back EMF is equals to the half of applied voltage. So this is the condition for attaining maximum mechanical power. That is nothing but when the applied voltage is twice that of the back EMF, or your back EMF is half that of the applied voltage, we will get the condition for maximum mechanical power. So this is the required condition for maximum mechanical power. Moving on to the calculation of losses and efficiency. So before calculating what efficiency of a DC motor, we are going to first discuss about what are the different kinds of losses which occur in a DC machine. So we know that output of a DC machine is always less than the input. So why it is less than the input? Due to the losses which are occurring in the machine. So when we take the machine is acting as generator, we know that the input given to the generator is mechanical and the output drawn from the generator is the electrical. And when we consider about the DC motor, we know that the input given to the motor is electrical and the output drawn from the motor is mechanical. So in this process of converting one form of energy to other form of energy, we know that the input power is always less than the output power. This is due to the fact that there are some losses which occur in the machine inside. So coming to DC motor, the losses in the DC motor, we know that there are the same losses that occur in the DC generator except the power flow. We know that the input power and output power for both DC generator and motor are different. So that is why the losses are same, but the power flow from the input to the output terminals is different when we consider the case of generator and motor. So as the same machine can be used for different purposes, we know that DC motor converts electrical to mechanical and generator converts mechanical to electrical. So it is a fact that input power to the motor is in terms of voltage multiplied by current, which is in terms of watts, and it is not fully converted into mechanical power. We know that this is the horsepower multiplied by 746. We get it again in terms of watts. So what are the various kinds of losses which we come across in the DC motor are nothing but the copper losses, iron losses, rotational or frictional losses. These are mainly the three kinds of losses which we can encounter in case of DC motor. So which we are going to further discuss in detail. So copper losses, iron losses and the frictional losses occur during the power conversion, that is from, in the case of generator, it occurs during the power conversion from mechanical to electrical, and in case of motor, these losses occur in the power conversion from electrical to mechanical. So these losses, we know that they dissipate heat in the motor or a generator. So if the losses in the motor increases further, we know that the efficiency of the motor or generator will decrease. If more losses occur, it may lead to the burning of the motor or generator at all. So we know that for a better DC machine, whether it may be a motor or generator, the losses should be less such that efficiency will be high. So the first kind of losses, basically the losses in the DC machines are divided into electrical losses, magnetic losses and mechanical losses. Electrical losses are further again divided into three kinds: armature copper loss, shunt copper loss and series copper loss. So nothing but armature copper loss is the loss which is occurring in the armature resistance. Shunt copper loss is nothing but the copper loss which occur in the shunt field winding. Series copper loss is a copper loss which occur in the series field winding. So we have three kinds of electrical losses, namely together called as copper losses, which are occurring across the armature, shunt field winding and the series field winding. And then we have magnetic losses. Magnetic losses basically occur in the core, that is nothing but in the stator of your DC machine, whether it may be generator or motor. So iron and core losses occur in the magnetic poles which are fixed to the stator. We basically have two types again for the magnetic losses. First one is hysteresis loss and second one is the eddy current loss. And then we have mechanical losses, that is nothing but the losses which occur due to the friction and rotation. So the frictional loss and windage loss can be together considered under mechanical loss. So moving on to first, the electrical losses, nothing but the copper losses. So when the current flows through the conductors, that is nothing but whether it may be shunt field winding, armature winding or the series field winding, we get losses in terms of I square R. Due to the resistance of the conductors, we get the losses in terms of I square R. So whatever the losses we get across these three windings in terms of I square R is nothing but called as copper losses. These losses can be further classified as armature copper loss. So armature copper loss, it basically constitutes about 30 to 40% of the total full load losses of a DC machine. We basically know that they occur across the resistance terminals of the armature, that is nothing but RA. So armature copper loss can be taken as the current flowing through the armature, that is nothing but IA, and the resistance of armature, that is nothing but RA. So IA square RA is nothing but the armature copper loss which occur in the armature of a DC motor. Then we also have copper losses in the field windings. So we basically have two kinds of field windings. One is shunt field winding. The winding which is connected in parallel to the armature is called as shunt field winding, and the series field winding, the winding which is connected in series with the armature winding, is called as series field winding. So we know that they possess some resistance. Let us consider RSH as the resistance of the shunt field winding, and let us consider RSE as the resistance of series field winding. So the losses which occur in the form of the current flowing through the shunt field winding is ISS square multiplied by RSH will give the losses which occur in the shunt field winding, or the copper losses which occur in the shunt field winding. Series field current ISC multiplied by the resistance of the series field winding will give the series field winding copper loss. So we have the field copper loss for both the shunt field winding and series field winding based on the type of motor which we consider in series, whether it may be series motor or shunt motor or a compound motor. When the current flows to the shunt field and the series field, some losses occur due to the resistance of these field windings, which is called as field copper loss. So these field copper loss constitute about 20 to 30% of total full load losses, so which can be calculated by using these three formulas. So together we also have interpole winding losses. We know that the interpoles are the poles which are situated between the main poles to compensate the armature reaction effect. These interpoles also have windings which are wound on them. The losses which occur in these windings in the form of Ia square. R2, let us consider R2 be the resistance of interpole windings. So then we also have copper losses which are occurring in the interpoles. Then we also have brush contact resistance loss. So as the name suggests, these losses are nothing but they occur in the brush resistance. We know that the brushes are attached to the commutator. Commutator is nothing but the process of converting the alternating terminals to the direct terminals or direct current. That is nothing but converting AC to DC in a DC machine occurs in commutator. We know that the two brushes are attached to the commutator. So current reversal process takes place in the commutator, and also these brushes carry the DC current to the external load connected to the commutator. So there is some resistance for these brushes. So the drop which occurs across these brushes is also considered as the brush contact resistance loss. So totally we have the total copper loss in a DC motor can now be given as the sum of the copper loss which are occurring across the armature, which is occurring across the shunt field winding, and which is occurring across the series field winding. Next kind of losses are nothing but the magnetic losses. We know that the magnetic losses always occur in the core or the iron core. So these magnets, the main field poles, are situated in the stator terminals. So again, these magnetic losses are further classified into two types. One is hysteresis loss and the other is eddy current loss. So these iron losses or core losses constitute for 30 to 40% of the full load losses. Out of the total losses occurring in the DC machine, these iron losses or the magnetic losses constitute about 30 to 40% of full load losses. So the first one is hysteresis loss. We know that we have the process of hysteresis. We know that the BH curve. This curve is plotted between the magnetic flux density and the magnetic field intensity. So the process of magnetization and demagnetization of core will occur in a DC machine. So this and some amount of energy will be lost in the process of magnetization and demagnetization of armature core. So this kind of losses or the energy lost in the process of this reversal of magnetism or the process of magnetization and demagnetization is called as hysteresis loss. So each part of rotational core passes among the two poles, that is nothing but the south pole and the north pole. So when the rotor in the armature starts rotating, so what happens? It consequently passes through the different poles, that is north pole and south pole. So due to these polarity changes, the process of magnetization and demagnetization will occur for the flux which is being generated under the influence of main field poles. So due to this polarity changes, we get the energy loss in the terms of hysteresis loss, and also this hysteresis loss completely depends upon the flux and the speed of the motor. We know that EB is nothing but again 5 ZNP by 60A. Back EMF is again dependent on the flux and the speed of the machine. So that is why the energy lost due to this hysteresis loss is given in the form of W hysteresis, which is directly proportional to the magnetic flux density or the flux per pole, which is there under the influence of different poles in the stator, and it is also dependent on the frequency of the alternating quantities in the commutator, and it is also dependent on V, which is nothing but the volume of the core. So these are the dependent factors of the hysteresis losses, that is nothing but the magnetic flux density, frequency and volume of the core. Next magnetic losses is nothing but the eddy current loss. So when the armature core rotates in the magnetic field, we know that an EMF will be induced in the armature core according to the laws of electromagnetic induction. So nothing but the Faraday's laws of electromagnetic induction. This is a process which occur in any DC machine as the resistance of the core is low. That is nothing but, we can see that the core area or the armature core is usually of large area. So hence huge amount of current will flow and which causes the more losses. So we can see that from the resistance formula L by A. So when the area of cross section is more, the resistance is low. So the power loss due to this eddy current is known as eddy current losses. So the huge amount of current will now flow through this small resistance value of that core. So this small amount of current which is flowing through this resistance of the core is nothing but calculated as eddy current losses, which can also be called as the leakage currents or the currents which are flowing in the stator of your DC motor. So to reduce eddy current losses, we know that the losses occur in the form of heat. So we laminate the core with a proper insulation between the laminations. So the core used here is nothing but the solid core, which is made up of silicon steel in the DC motor. So to reduce this kind of losses, we use the laminations for the core. So the eddy current losses cannot be fully eliminated, but we can minimize it by laminating the core. So these losses, again the eddy current losses are again dependent on flux density, frequency and the thickness and volume of the core. Both the thickness and volume of the core. So eddy current losses are nothing but the losses which occur due to the leakage currents or the currents flowing in the core of the DC motor. So when these leakage currents flows through the resistance in the core, the losses which occur are called as eddy current losses. Both the eddy current losses and the hysteresis loss together called as the magnetic losses. Then moving on to the constant losses or the constant losses in the DC motor, which is nothing but the mechanical losses. The mechanical losses which occur due to the rotation. The rotating part in the DC motor is nothing but the armature. So mechanical losses are also known as frictional or rotational losses. So these losses can be further classified into frictional loss, windage loss, stray loss. So the losses which occur due to the friction between the surfaces of brush to the commutator and bearings to the shaft connected to the armature are called as frictional losses, and the windage losses are nothing but when the natural air, we know that a proper air gap is being maintained between the stator and rotor of your DC motor. So when this air opposes the rotation of armature, this rotating armature needs to be pushed against the natural air which is coming for the cooling purpose. So this small amount of losses which opposes the rotation of armature are called as windage losses. Stray losses. So the frictional losses and the iron losses are now known as the stray losses. So stray losses can also be considered as the losses which occur due to the insulation also. So all these losses constitute a very low percentage of the total full load losses. That is nothing but the frictional and windage and the stray losses which occur in the DC motor constitute a very low percentage, that it may be up to 1 to 2% of the full load copper loss. So now we can take the magnetic losses and the frictional losses as the constant losses and the only variable losses which occur in the machine are called as copper losses. So from this, the variable losses are the copper losses which are occurring across the armatures, series field winding, shunt field winding, and the interpole windings. Total losses can be given as a sum of constant losses and variable loss. Constant losses are the losses which are occurring in the core and the rotational losses. The core losses and the rotational losses together can be considered as constant losses, and the variable losses are nothing but the copper losses. Now we got to know the different kind of losses which occur in a DC motor. From this, we can calculate the efficiency. So let us see the power stages in the DC motor. So now we know that the input energy to a DC motor is nothing but the electrical energy, and the output is nothing but the mechanical energy. So in between the process of conversion of electrical to mechanical, we have seen different losses occur across the different parts of the motor. So for this reason, we know that the output of the motor will always be less than the input power. So all the DC motor losses during the energy conversion at different power stages is seen in this picture. We can see that the motor input is the product of the applied voltage and the current from the line terminals. So once this input is given to the motor, we can see that the copper losses occur in the armature terminals. So the mechanical power developed at the armature is nothing but the product of back EMF multiplied by the armature current. So this mechanical power, we see that the shaft rotation, the frictional and windage friction is involved at this stage of power. So we can see now iron and friction losses here occurring in the core of the armature. So the output delivered to the load will be now mechanical power in the form of horsepower. If we want to convert it into watts, we multiply it with the 746. These are the different power stages in the DC motor. Coming to the efficiency of DC motor, efficiency is defined as the ratio of output power to the input power, which is multiplied by 100. So we can give the output power as input minus losses. We can write the output power as input power minus the losses, and input power as output plus losses. So therefore, the efficiency can now be written as using these two equations, that is equation 1 and 2. We can write input minus losses in place of output power, or output plus losses in place of input power. And we can write the efficiency equations in this way. So together we can say that efficiency is the ratio of output power to input power. So now we have to derive the condition for attaining the maximum efficiency in a DC motor. So we know that efficiency is affected by the losses which are occurring in the DC motor. We have seen the different kinds of losses. So now for this, let us consider a shunt motor. In shunt motor, the shunt field winding is connected in parallel to the armature. So let us consider it is drawing IA amperes of armature current, and the back EMF developed across the armature is EB. So now when we write the input power as output power plus variable losses plus constant losses, we know that the variable losses are the copper losses and the constant losses are the magnetic and rotational losses. So from this we can further write the equations for efficiency as EB into IA, which is nothing but the output power or the mechanical power which is developed across the shaft of the motor. And now I'm writing the input power as output power plus the losses. So output power is again EB into IA, variable losses as the copper losses, and constant losses I'm writing it straight away as WC. So now when we divide this entire equation with the term EB into IA, we will get the efficiency as shown in the equation 3. So when we differentiate this particular equation 3 with respect to time, that is nothing but dt, we get the condition for attaining the maximum efficiency. So upon differentiating this equation, this is in the form of u by v. From u by v, we know that differentiation of u by v can be written as u into v dash minus v into u dash divided by v square, which is equated to 0. So this particular term, the denominator, IA into RA by EB plus the constant losses divided by EB into IA. This is EB into IA. Differentiating this whole term with respect to t and equating it to 0. This particular term, we get it as usual, IA into RA by EB plus as this is a constant term, so this particular term will become 0, and when we take the denominator and equate it to 0 on the right hand side, we make this term also equated to 0. So we are left over with this particular term. When this particular term is differentiated with respect to IA, we get the equation as RA by EB, the first term, and constant losses term divided by EB into IA square. So when we bring this constant term to the right side, we get a condition that is nothing but when the constant losses is equals to the variable losses, we can attain the maximum condition for the efficiency. Therefore, the maximum efficiency occurs in a DC motor when the copper losses are equals to your constant losses, that is nothing but the magnetic and rotational losses. Thank you.